Alright, so I'm going to do part A of 8.5.6 in this video. It says to find the third order Taylor polynomial for the function x to the third minus 2x squared plus 3x minus 1, centered at a equals 0. And then we're supposed to say if our answer surprises us and to explain why. So I wrote out the table to find the coefficients for each term in the polynomial. So for example, the 0th term, you're basically taking the 0th derivative. That's just going to be the function itself. And you're evaluating at a, which is 0, so you just get negative 1. And then you're dividing it by the 0 factorial, so you just get negative 1. Then for n equals 1, you just take that derivative. You do the same thing, you get 3. Take the next derivative, you get 2. Take the next one. And finally, you get 1. So then here is sort of the general equation for our Taylor polynomial. So then when we go and put our values in, we're getting our f of a is negative 1. Our f prime of a is 3. And then it goes with x because the a just goes away. Then our f double prime is negative 4. So negative 4x squared over 2 factorial, and then plus 6x to the third over 3 factorial. And then when we simplify it, we get negative 1 plus 3x minus 2x squared plus x to the third, which is just our function. So at first this really surprised me, but then it actually makes sense once you think about it. In other words, what it's saying is that the third order polynomial is the function itself. So it's 100% accurate. And the reason this makes sense is because what Taylor polynomials are doing is they're matching up even better and better for each iteration. They're matching the derivative and then the derivative after that. So for the t of 0 of x, we're matching f of a, and then for t1 of x, we're matching f of a and f prime of a, and so on and so forth until you get t3 of x. Well, that matches f of a, f prime of a, f double prime of a, and the third derivative of f of a. And for polynomials, the thing about them is that you really can only take a finite amount of derivatives until there's nothing really left to take, right? So once we do the third derivative, we're left with a constant. So after that, we're just getting zeros. So for Taylor polynomials, or for polynomials, you're just sort of like whittling them down until you're getting this constant. And so that's not the most beautiful explanation, but that's sort of how I intuitively thought about it, is that you're just matching, whittling it down until you get that constant, and then there's really nothing left to match because then you're just getting zeros after that. So I think that's part A, and I'll do part B and C in the next video.